Hi, welcome to this video. With reference to the previous video, the same unit, we are going to discuss cardiac and respiratory therapy equipments. In this, we are going to see the programmable pacemakers. Here, it consists of two parts. One is external and the internal part. The external unit which generates the programmed stimuli which is transferred to an internal unit by one of the several communication techniques. So it shows the functional block diagram. It is having a magnetic, radio frequency and acoustic ultrasonic pressure waves. Usually the magnetic and electromagnetic is placed on the surface of the body and it establishes the magnetic field, whereas radio frequency waves, the information can be transmitted over a high frequency electromagnetic waves, whereas acoustic ultrasonic pressure waves from a suitable transducer placed over the skin and it can penetrate into the human body. So out of all these methods, we can go for the magnetic field method. It is most widely used because of the simplicity and minimal power requirements. That is very important one. Usually, essential requirement of the programmable pacemakers is that they should be immune to the accidental programming from naturally occurring energy sources. So to meet all these requirements, the information is usually coded in the pacemaker and it contains a decoding mechanism to recognize the proper given information. So this programming security code method makes it practically impossible to reprogram an implantable pacemaker through an extraneous random magnetic fields. Okay, so this is all the important discussion while going for the programmable pacemaker. So this shows the multi-programmable. That's why we can go for the multi-programmable pacemaker. So the block diagram contains the system 1, system 2 and system 3. So you can see system 1, system 2 and the system 3. Okay, so usually the system 1 controls the main timing function, timing control and the rate limiter, and there is one output circuit and the stimulating function of the electrode, whereas system 2 that is operating as directed by the programmable control circuit. This system generates the output pulses at the programming rate, width and amplitudes unless overridden by the system 2. Whereas this system 2, it contains a sensing signal discriminating function of the circuit, comprising the sensing function of the electrode, an RF filter, signal amplifier and one comparator. Okay, and one comparator. This system identifies the signals of the cardiac origin, where it comes and where appropriate, and sends an inhibit signal to the system 1, this path. Okay, whereas the final system 3 carries a programmable control circuit that validate the circuit and read the switch and master the timing crystal. So this is the overall idea of this multi-programmable pacemaker. Usually under normal conditions, the timing control circuit periodically triggers the output circuit, causing the emission at the programmed rate of simulation pulses of programmed pulse width and amplitude. So the period between each trigger signal is scrutinized by the rate limiter, and an unlikely event of component failure causing the rate increase, the limit holds the rate of simulation to less than 180 bpm. So upon the receipt of this inhibit signals from the system 2, the timing control compares the time arrival of against the programmed refractory period. So the signals arriving within the refractory period are ignored. Once again, the signal is detected by the filtered is at a high frequency components by the RF filter. The signal is then selectively amplified by the amplifier by an amount determined by the programmed sensitivity level, and the resultant signal is compared with the preset level of the comparator. Signals of either polarity with magnitude greater than the preset level enables an input signal is fed into the system 1. Okay, and the remaining signal preset levels are ignored. So this system 3 acting on programming signals are transmitted to the reed switch, directs the pulse generator to function as programmed. So the reed switch, by opening and closing in sympathy with the magnetic pulses emitted by the programmer, feeds the signal to the data, validate the circuit. After first verifying that reed switch was closed for a minimum period of 300 milliseconds, so the data validate circuit checks and execute a code validation check. Only when all these checks are satisfied is a programmable control circuit directed to store the new code. By activating the appropriate electronic switches, the programmable control circuit directs the system 1 and the 2 to implement the new program conditions. So the pulse generator is non-invasively programmable by means of programmer, which emits the magnetic code that enables the following parameters to be altered. Very note down: rate, pulse width, pulse amplitude, sensitivity, refractory period, and hysteresis. So all these measures are taken at 37 degrees centigrade with 500 ohms resistive load. Once the programmer contains microprocessor based transmitter or receiver that operates by inductively coupling pulse position modulated binary coded data from the programmer via the programming WAN to the pulse generator. So the programming information is contained a 20-bit command code specifying the desired rate, pulse width and pulse amplitude, sensitivity level, mode of operation, pulse generator model of identification code, and check codes. If an attempt is made intentionally or unintentionally to include the programming command, a parameter that is not a feature of this pulse generator being used, so that parameter will simply remain at its nominal value. So all validly reprogrammed parameters in the command will be implemented. So this is a part of the command code, is a check code. If this check code is not correct, the command is rejected by the pulse generator. So the timing of the transmission is precise, a very important one. So the crystal oscillators in both the programmer and the pulse generator controls the frequency of data exchanges. Each data bit is transmitted within the approximately 1 millisecond. So the entire command code and the complement are transmitted within the approximately 40 milliseconds or 1/25th of a second. So this is a usually programmable pacemaker. Okay, so that's all about your pacemaker. Next, coming to the cardiac defibrillator. So before going to discuss the DC, that is different types of defibrillators, once again we are going to discuss why we need the DC, this kind of defibrillator. Usually the ventricular fibrillation is a serious cardiac emergency resulting from asynchronous contraction of the heart muscles. This uncoordinated movement of the ventricle walls of the heart may result from coronary occlusion or sometimes abnormalities of the body chemistry. Because of this irregular contraction of the muscle fibers, the ventricle simply queer rather than pumping the blood effectively. So this results may steep fall or sometimes takes the that is the patient can prove the fatal or if adequate steps are not taken promptly. So this is in fibrillation. Main problem is that heart muscle fibers are continuously stimulated by the adjacent cells, so that there is no synchronized succession of events that follow the heart action. Consequently, control over the normal sequence of the cell action cannot be captured by a ordinary stimuli. So when you go for the ventricular fibrillation, can be converted into more efficient rhythm by applying a high energy shock to the heart by means of external instrument. So this sudden surge across the heart causes all muscle fibers to contract simultaneously. Possibly the fiber may then respond to normal physiological pacemaking pulses. The instrument for administering the shock is called the defibrillator. So this portion, So these are having some problem. So once again we are going to give a high voltage shock. So we are getting a normal ECG pulse. So the shock can be delivered to the heart by means of electrodes placed on the chest of the patient by means of external defibrillation, or the electrodes may be held directly against the heart when the chest is open, that is internal defibrillation. So the higher voltages required for external defibrillation than the internal defibrillation. Kindly note that there is some difference. So implantable defibrillators are also available for the patients who are at a high risk. So this is the main idea of why we need the defibrillator. So based on the types, that's just now we have seen, that is types of defibrillator, that is external or internal. Once again it is classified into AC and the DC defibrillator. So these are all the diagrams. What is defibrillator, you can easily identify. So coming to the AC defibrillator, a resistive and a simple capacitive network is or monostable multi-vibrator forms the timing circuit. So it's having a AC supply. Once again it's having a one step up transformer, and they are connected to the resistive and simple capacitive network or monostable multi-vibrator, the timing circuit. So it is triggered by with a foot switch or a push button switch. So various tapping are available along the secondary winding. They are connected to the electrode that delivers an electric shock to the heart of the patient. Voltage value ranging from 250 volt to 750 volt. Okay. In the AC external defibrillation. For safety reasons, secondary coil should be isolated from earth to avoid the shock. For internal fibrillation, voltage values from 60 volt to 250 volt. So to produce a uniform and simultaneous contraction of the heart muscles, large currents are used for external defibrillation. So this is a resistive simple capacitive network in the AC fibrillator. So coming to DC fibrillator, it is having a so the DC defibrillator doesn't produce a side effects and produce a normal heartbeat. So ventricular fibrillation is avoided when a high energy shock is passed through the discharging capacitor that is exposed to heart or chest of the patient. So DC fibrillator contains a T1 transformer and the T2 high voltage transformer. A diode rectifier, diode is used to rectify the output voltage from the transformer. It is connected to vacuum type high voltage over the switch. At position A, usually we can know that one end of the capacitor is connected to the one end of the capacitor. Automatically at position A, the capacitor charges, okay, to voltage applied. A foot switch present on the handle of the electrode is used to deliver a shock to the patient. Now a high voltage switch changes its position from A to B. That makes a capacitor to discharge to the heart via electrodes. To slow down the discharge from the capacitor, an inductance is used, that is to control the discharge path. An inductor is used to place in the one of the electrode lead. So this L induces a counter voltage that reduces the capacitor discharge value. So this is the idea of DC defibrillator. So next one, so defibrillator analyzer. So this diagram shows the DC defibrillator analyzer. So a DC defibrillator analyzer is basically meant to measure the energy content in the discharge pulse. So it works on the principle that the energy contained in a pulse of arbitrary shape and time duration. It is given by E is equal to integral 0 to t E of t I of t into dt, where E is the energy in watt seconds, E of t is a voltage as a function of time, I of t is a current as a function of time, and t is the time duration of the pulse. When the voltage exists across a fixed resistance, the energy dissipated is 1 by r 0 to t, that is integral of 0 to t, E of t the whole square into dt, where r is the resistance of the load. Okay, so this diagram shows the block diagram of a defibrillator analyzer. So this defibrillating pulse is applied to the across a 50 ohms resistor load, and the voltage developed across it is given to the squaring circuit. So the squaring circuit consists of a 4-quadrant multiplier followed by an op amp. So the output of this device is a current which is proportional to the product of the two inputs. In the squaring mode, the two inputs are connected together so that the output is a square of the input voltage. So op amp acts as a current to voltage converter, producing an output voltage which is proportional to the output current from the multiplier. Besides this block, so there is a defibrillator analyzer contains other circuit for controlling the measurement of the operation. For example, pulse integrator circuit that integrates the squared function during the time that pulse is present. So during the remainder of the display time, it acts as a analog storage element. So the voltage stored in the pulse integrator is read on the energy meter calibrated in watt seconds. So thank you.